Okay, so good morning, everybody. I'm very happy to welcome you, and I'm very happy to introduce today's Lumer lecturer, Simone Göttlich from University of Mannheim. So she studied mathematics at Technical University of Darmstadt, and so I'm also, since I'm at Darmstadt, I'm also very happy about this. And then she moved to Technical University of Kaiserslautern for her PhD and habilitation degree, and she's an expert in mathematical modeling, numerical analysis, hyperbolic conservation laws, in particular on networks and also on optimization. And yeah, I think she's really one of the experts on hyperbolic problems on networks, their optimization, also non-local effects. So I think this very, very nicely ties in with the research goals and scope of our network. So I'm extremely happy that we could convince her to give a talk here, and I would like to hand over. So please go ahead.
Thank you, Jan, for this kind introduction, and thank you all for having me. So today I will speak on scalar conservation laws on networks, as you can see here on the first slide. And let's dive into the topic. A short overview of what I'm going to present within the next, let's say, hour. You see there are a lot of issues that need to be discussed in this network setting. And I will guide you through all these points step by step. So don't be scared so far. So let's start with this kind of introduction or motivation you see on this first slide. As a picture which is taken from this nice overview article by Bressan, Carnage, Garavello, Hertier, and Piccoli, which is called Flows on Networks. And this is actually the thing I'm going to discuss today. So you see there are several categories of applications like transportation, services and supply, and biomedical applications. And if we would now pick one of these pictures, you probably have a clear picture in mind of what's behind this. So if you think of gas pipelines, so interconnected pipes where some gas is flowing through, or think of these kind of irrigation channels, water canals, for example, where water flows and is divided into several other channels again. Or let's say production networks where you see here that several steps have to be performed during a production process, that the goods are delivered to the customers. Or, for example, blood circulation. If you look at the body, how the blood is pumped through our body in each direction. And one also very famous example are the so-called vehicular traffic flow models. Everyone is, I guess, familiar with the traffic, which you can observe outside. And this will be the key intention of my talk today. So what have all these applications in common? So, of course, they describe a so-called flow on a network. And the application, as we have seen on the slide before, are very fruitful in the sense that there are interconnected systems, and they are all characterized by a special kind of dynamics. So again, here you see on this picture on the right, the highway system of Germany, so which is highly connected. And whenever you observe a blue region, you know there's less traffic. And if you observe these high density regions in yellow or red, you see there's a lot of traffic around these big cities here. So, and the common features of all these kind of applications is the following. They describe transport processes. Transport in case that water flows through a channel, gas is transported, cars are driving, goods are produced, and so on. And therefore, we assume that we can characterize, in the case of a network, the edges by this kind of transport process given by hyperbolic conservation laws. Of course, there might be other ways of modeling. For example, you can go down to ordinary differential equations, do the modeling on that level, or think of other equations like particle methods and so on. But anyway, so the description here follows some hyperbolic conservation law. And the crucial point is, in all these applications, how to couple these different hyperbolic conservation laws at the nodes of the network. So whenever there are different edges connected, how to describe the correct mathematical framework. So this is the crucial point in all these applications I mentioned here. So very roughly speaking, we say that first of all, a network is a directed graph, consists of edges E and vertices V. We say that each edge in our network is parameterized by an interval AB. So there's some spatial, let's say, area. And this is one-dimensional, okay? Also very important. In the way of modeling, we have in mind there's only one space dimension later on when we really go through all the mathematical ingredients. So, and the dynamics on each arc is given by some conservation or balance law. So this is in particular important for applications like gas flow. So, and these conservation laws or balance laws describe the time and spatial evolution of conserved quantities on each edge. So, and this depends now if we only consider one conservation law to describe the dynamics, or if we would consider systems of conservation laws. I can tell you here, today I want to restrict on one conservation law, only describing the dynamics. Okay, this would be enough to go through all the details that are needed for the whole network setting. So, and again, the dynamics have to be coupled at the vertices at these points here whenever arcs, let's say, go into some intersection. And this corresponds to the idea that we have to consider coupled boundary value problems for the conservation laws we have in mind. Okay, this is the rough picture of all the things I want to speak on now. So let's go to some necessary definitions of all the ingredients we have seen so far. So first of all, as I told you, we are only concerned with one conservation law on each edge. That's why we restrict to this case of scalar conservation laws. And we say that we have some rho given by this mapping here and some f, and these two are functions, and we call this equation here a d-dimensional scalar conservation law. So this is a very general definition of conservation laws. And I can tell you that the terminology scalar is not uniquely defined in the literature. Okay, that's important to know. When I talk on scalar, I mean that we restrict to one conserved quantity. This would be here our rho on a d-dimensional spatial domain. Okay, but I've already told you that in the case of networks, we are mostly interested in equations that correspond to only one spatial dimension. That's why d equals 1 is the setting from now on. So, and that's why we say that this rho is nothing else than the density in our setting. So roughly speaking, and again, going back to this conservation law, we have a closer look at this kind of equation here. So meaning that... Sorry? Okay. So if we look at this equation, we see we have one equation for two unknowns, which are rho and f, okay? So this means that this equation is not closed, and we need to know how the relation between f and rho may look like. And the simple choice you may imagine is that we choose f equals to a times rho. And this would exactly lead to the well-known advection equation with the direction or with the velocity a. So, but this gets more involved when we talk about traffic flow in a minute. So, and we see, if we have a look at the conservation law again, that every function that is rho identical c for some constants would be a solution. So we need additional requirements on the density on our rho, like, for example, initial conditions. And whenever our conservation law is equipped with an initial condition, we call it Cauchy problem. So therefore, again, we restrict to a domain here and some time interval of these types. And we say that this would be our Cauchy problem. And this rho 0 would be our initial condition. So again, you could ask, what about boundary conditions? This would be also an interesting topic. So far, we don't talk about boundary conditions, but we come back to this point when we talk about the network setting. So having all these definitions in mind, let's talk about traffic. So as I told you, I want to introduce some traffic network flow model. And one very popular model is the so-called Lytle-Witham-Richards model, LWR model, which was developed in 1955 or 1956 independently from the two guys Lytle and Witham and Richards. And what they did, they described the evolution of the traffic density at some position x and some positive time. And the crucial point is that they put several assumptions now on this flux function f of rho. And these are important from now on, since they mainly drive the discussion on the properties of the traffic flow model. Okay, let's go through step by step. First of all, we say that this flux f at 0 is 0, meaning that there are no cars entering or leaving, so no flux. And if you look at the highway, you would observe that there's a maximal density possible on the highway. And whenever this maximal density is reached, the flux gets stuck, meaning this is also 0 and would correspond to a traffic jam, you may imagine. So furthermore, we say that this f of rho is positive for the density in our interval 0 and rho max. F is 2 times differentiable and strictly concave. So these are the key assumptions that are necessary for the Lytle-Witham-Richards model. So, and what's so crucial about this? Those assumptions really ensure the existence of a maximal density, which is now encoded by this rho star, such that F takes its maximum there. So, and using now the average speed of cars denoted by this V of rho, it's common to write that the flux can be written as the velocity times the density. So what does it mean? If we go ahead, we can now say that there's a special kind of flux function fulfilling all these assumptions I showed you before, and which is reasonable for traffic flow. And this flux function is essentially given by this rho max times this 1 over rho divided by rho max times rho, meaning that this expression here is nothing else than our speed function. And you see, if we would have a look at the picture here where rho is plotted against the velocity v of rho, in the case the density is 0, so cars can drive with their maximal velocity. And then there's a linear dependence, and once the maximal velocity is reached, the velocity is 0. And finally, if we look at the left picture here, we see this is called fundamental diagram. The concave shape of our flux function with a maximum here at rho max half, saying that we have essentially two regions of traffic. The first one here is called free flow. The second one here is called congested regime. Of course, there might be other ways to state such a flux function, but here in this talk, I will stick to this well-known Green-Shields flux function. And normally, like we do later on, we normalize this kind of flux function in a way that we say the maximal velocity as well as the maximal density are set to 1. What about solution concepts now for this kind of traffic flow model? What's behind? So I think it's important to mention here. So otherwise, it's hard to follow the discussion on the different types of the solution that might occur if we directly would skip into the network setting. So again, let's have a look at the conservation law here. And let's assume that we have an infinitely long road and the spatial domain to be the real line. Furthermore, we say that rho should be a function from C1, and we introduce so-called characteristics in the sense that if we have a look at the total derivative here of rho x of t and t, we see that this would be, let's say, the derivative we can compute. And on the other hand, we also know from the conservation law above that this can be written in this way here, meaning that this f prime is taken out of the convection term. So now, what does it mean if we now compare these two kind of expressions here and here? We can say that this derivative of x of t equals f prime, and we say that the total derivative of rho is 0. So, but in other words, this means that this rho is constant along the characteristics. And this leads to the interpretation that the characteristic satisfies for this kind of initial data that this equation here is fulfilled. And this is nothing else than an ordinary differential equation, where the right-hand side is independent of t. So now we can integrate and write down the solution of the characteristic given by this equation here as straight lines, where the information about the flux function dependent on the initial value is needed. So what else we should be aware of? So for a given pair, which should be here x star t star, we want to derive the value rho of x star t star. So, but now we know that the solution rho is constant along the characteristic, as we have already seen. That's why we have to take the characteristic crossing x star t prime to go backwards along this characteristic until the initial data is reached. So, and having this idea in mind, we can define some mapping phi given by this expression here. And we obtain that the value we are interested in this rho of x star t star can be expressed via the definition of our phi above. So, and what should we learn here? So the equation is well defined if this guy here exists. So, but now the implicit function theorem ensures in an open neighborhood of x star the existence if this here is fulfilled. So what does it mean in case of our traffic flow example? So again, let's consider the flux function. You see here the normalization. So Vmax and rho max are 1. So f of rho is given by rho times 1 minus rho. Then we can compute the second derivative, which is minus 2. and we can insert in the calculation we have done so far. And what we see is that for t equals this guy here, provided that the partial derivative with regard to x of this row 0 is not 0 in a neighborhood of x, that there exists a x with these properties here that ensures that our phi is only invertible around x for this given time interval. Okay. So what should we learn from this example here? I'll show you a picture in a minute. We see that a C1 solution cannot exist for any arbitrary fixed time interval. So the assumption we put on our density rho is too strong, since, as we will see, the characteristics will cross and the solution may collapse. So in particular, for the special choice of the initial condition to be x, we see that the characteristic in the xt plane will cross at the time t equals 0.5, as we see here. And this would directly lead to a new solution concept for this kind of traffic flow model we have in mind. So that's why from now on, we go over to weak solutions. So if you have a look at this definition here, we say that a weak solution to the Cauchy problem is given if for a continuous mapping here rho, and for every test function phi, we have that this condition is fulfilled. So this now weakens somehow the assumptions on our rho, and may also be useful to consider non-smooth solutions, as we will discuss in a few minutes. So what's very important in this kind of equations is to consider special problems to study these weak solutions that might occur. And the simplest non-trivial functions to study weak solutions are initial values given by two constants, rho L and rho R, in the case that these are piecewise constant functions defined on this spatial domain. Oh, no, this should be rho, sorry for that. And these kind of problems are called Riemann initial conditions. And if we would now use these Riemann initial conditions and combine them with the conservation law, we are talking about a Riemann problem. So, and now, very, very important to mention which solutions may occur now. So one can show, using the definition of weak solutions, that one solution is given by a traveling shock discontinuity, meaning that the solution rho of x and t is given by rho L and rho R. So in the setting that if we now have that either x is smaller than s times t or larger, what does it mean, this kind of s? So again, we have a weak solution, and S is now the so-called ranking-Hugoniot condition, which is given by this equation here, and which is also called the shock speed. So you can believe me or not that this is a weak solution. So I don't want to go into the computational details, but anyway, you can insert this weak solution into the definition and really compute that this is a weak solution under this condition given here by this ranking-Hugoniot condition. A further weak solution is given by the so-called rarefaction wave. And the rarefaction wave is now given by this expression here. Again, we have different regions of solutions, so rho L, rho R, and something in between, which is given by the inverse of our derivative of the flux function. And the condition that f prime of rho L is smaller than f prime of rho R. So, and by assumption, we know that this f prime is strictly monotone decreasing and that the inverse exists. So this was one of the assumptions we put on the flux function. So, but again, this is a weak solution. You could insert into the definition of weak solutions and really compute out of this definition that this is a weak solution. But so far, we have given now 2 weak solutions, but we cannot ensure uniqueness so far. So, and to come up with a topic of uniqueness, we need a new concept to really extract the physically correct solution. And this is now the weak entropy solution. So, and this is given by the definition of Khrushchev entropy admissible conditions. If you check here, the definition, it looks similar to what we've seen before for weak solution, but is a bit more involved. So what does it mean now, this Khrushchev type of entropy solution? So in fact, there's a theorem saying that rho is a traveling shock discontinuity, whereas so the shock speed satisfies the Rankine-Hugoniot condition, and then rho satisfies the Khrushchev entropy admissible condition if these 2 conditions here are fulfilled. So maybe it's not that clear at the first glance, and this would also a very longer story to go into all the details of entropy solutions. But anyway, maybe we can check for the remark above to see what does it mean for the traffic flow model. So for the traffic flow model, we know that we have a concave flux function and the following implications hold. So in the case that rho L is smaller than rho R, we see that the derivatives are given in that way, and we would end up with a shock solution, so a traveling shock. And in vice versa, if now rho L is larger than rho R, we have here the other implication, and we see we would end up with a rarefaction wave. So this is important to mention again. There are 2 different kinds of waves occurring in this kind of traffic flow model we are going to investigate. So let me explain about these 2 things, some details in these 2 pictures. Also on the left, you see the characteristic plot for the case that we have a traveling shock discontinuity. This would be here if we go to the right picture, where we see that rho L is smaller than rho R in the beginning. So for the initial condition, t equals 0, and we see some transport of this shock with a positive velocity in that case for the next time step, t equals 1. Meaning going to the left again, we see the characteristics cross, and this crossing of characteristics means that there's a shock front propagating through our system. And, oh, sorry, if we go to the rarefaction wave, maybe we start again with the right picture. We see again these 2 kind of states, rho R and rho L. Here rho R is larger in the beginning for t equals 0, and we see if this initial condition starts to propagate, we end up with a rarefaction wave, and we have the state rho R again. We have something in between, and we go down to rho L. Meaning, if we go into the picture of characteristics, we see actually 3 regimes. So one regime here corresponding to rho R, one regime here corresponding to rho L, and something in between. So there are maybe some lines missing, since there is a fan spreading out of this x equals 0, which means that this is the rarefaction. And this can be observed in the case of traffic by this state here. And in the case of traffic, this is a straight line. For other applications, this might be something different. So why it's necessary to studying these Riemann problems so intensively? So first of all, it gives you a good picture of which kind of solutions we can expect if we would consider more complicated initial data. So further, it's the key point, the key ingredient somehow to prove the existence of more general solutions applying the wavefront tracking technique. I come to this point in a few minutes. And based on the idea of Riemann problems, we can construct in a very straightforward way also a numerical approximation to numerically solve our conservation law. And this approximation is called the so-called Godunov scheme. So again, the idea of wavefront tracking, just to give you a picture, is to say that if we now have initial data in a very general manner, we can assume that this initial data can be approximated by piecewise continuous functions. So here, let's say this would be our row 0, and then we have these piecewise initial step functions. And at each of these problems, we can now solve again Riemann problems, right? So meaning that we really construct a sequence of approximate solutions where we know that these might be either shocks or rarefaction waves. And this helps to do the following. So we can estimate the number of waves, and we can also estimate the number of interaction between these waves, since they might collide when time evolves. And what's very important now in this procedure of wavefront tracking is to estimate the total variation of the approximate solution. So what do we mean by total variation? We say that total variation is explained or given by this expression here. And what is more important to mention is that the set of all functions with bounded total variations is defined as BV. So, and summing up all the facts I've showed you is that for some special initial data row 0 and the flux function f is Lipschitz continuous, we can conclude that there exists a unique weak solution row to the Cauchy problem of traffic flow satisfying the Khrushchev entropy admissible solution. And this full proof of this kind of theorem is based on this wavefront tracking I roughly explained before. So far is that we know how to deal with solutions on a single line. So what about the numerical scheme we can use for simulation purposes? Is the Godunov scheme, meaning that, again, restricting to the single line, we can build up a numerical approximation by solving Riemann problems. We introduce some spatial discretization given by these intervals here, and some cell interfaces points given in that way. Again, we need to think about the time discretization, and important to mention that we also need some CFL condition named after the guys Courant, Friedrich, and Levy. So meaning that there's a restriction on the step size, on the time step size given by, let's say here, this minimum over the delta x divided by the maximum of f prime. So what's the idea on the Godunov scheme? So we say that this rho ij denote the cell average constructed at tj in cell I. And the cell average, in fact, is given in that manner here. And if we would now think of a numerical scheme coming out of these ideas, we can say that if we consider the update for the time level j plus 1, we say that we have to compute the cell average at the time level tj. And then we add and subtract the fluxes at the interfaces we aim to consider. And this can be done due to the conservation of mass. And this leads you somehow to this expression here, which is, let's say, yes, the idea of the Godunov scheme. But again, there might be a problem, or there's something more going on, since we have to determine this rho star to get the right flux values to evaluate the scheme. And now the Riemann solutions, or the Riemann problems, come into the play. Since, okay, we can think about if this last equation is valid, but this is due to the construction okay. So we have step sizes according to the CFL condition. We have piecewise constant initial data. And we need to know these rho star dependent on the values of rho L and rho R at each of these interfaces. So what you see here is a collection of possible values that might be chosen for rho star. And this way of values correspond to the exact solution of the Riemann problems of the cell interfaces. So behind this closed formula, there is a detailed discussion of each of these kind of Riemann problems. And there comes out which value is the right one for the Godunov scheme to get it run. So, and again, a small picture we have in mind. You see these interfaces here between all these different cells. And we start with initial values here. Here they are again piecewise constant. And we have to check for the Riemann problems at the interfaces, meaning this is one Riemann problem. Another Riemann problem would be these combination, and the third one, these two. And once we have evaluated these Riemann problems, we can compute the next time step given by this solid line. So this would be a solid line for t equals 1. And again, we are then able to compute new Riemann problems and repeat this procedure until we reach our final time horizon. So now we have everything that is necessary to think about networks. So, and the network extension now is the following. We assume that we have a collection of arcs, and we also assume that there's a kind of LWR dynamics given by a conservation law of each of these arcs. And now, what is the challenge? What happens here at the intersections? Okay, and you see there are essentially two types of intersections. So one is we have one ingoing and two outgoing arcs. And the other one is we have two ingoing and only one outgoing arc. And this would characterize the main two types of intersections we have to think of. So again, what's important to know, we have a directed graph, and there are two sets denoting either the set of all incoming and or the set of all outgoing arcs for every vertex. So, and whenever we have more outgoing than ingoing arcs, we have to think about distributions of the traffic among these outgoing arcs or edges. That's why we introduce a distribution matrix A, given these entries here. And each of these entries now denotes the proportion of traffic coming from road I and going to road J. And we further assume that here the sum over the alphas, where the summation is over J, equals to 1. So now what's so crucial about these networks? So it's a notational mess in my mind. So it's easy to explain somehow, but it's not that easy to write down. So what do we need? In fact, we need to cover all or copy all the things we have learned for the conservation law on a single line or on one space domain, on one interval now to the network setting, meaning that we first need a notion of weak solutions. So, and the weak solution is now, if we consider a junction, a collection of functions rho that are either given by this rho in or rho out definitions. So again, this is simply, if we would reduce it to what we have seen before, the same notion of weak solution for one line only. And we need for the collection of test functions that they satisfy some node conditions given in that way. So what else do we know, or can we conclude? So if we consider a weak solution of ingoing and outgoing rows at a vertex, where the row in and row out combinations are given from these or are functions of bounded variations, then rho satisfies the ranking Huguenot condition at the junction, which reads as follows. So what does it mean? So we here on the left-hand side, we sum up over all the incoming fluxes. And on the right-hand side, we sum up over all the outgoing fluxes for almost every t. So this means, in other words, that there is mass conservation or flux conservation at nodes, okay? No cars will get lost or will be produced at nodes. So, and this leads to the definition of an admissible weak solution. So really, again, the crucial point is now thinking of what happens at the junction, okay? So the solution concepts for each individual road is clear. But anyway, what does it mean to consider now the combination with the junction? So the first point that is that we assume that at the junction we have these BV data for in and outgoing junctions. We further assume that the rho is a weak solution at the junction. We also have the distribution of fluxes among the outgoing arcs. That's why you see here the conservation of mass is more more written explicitly in the way that the alpha or the distribution parameters are included. But anyway, this is not enough so far to discuss the concept of solutions at nodes. Therefore, condition 4 is really necessary, which tells you that we have to maximize the ingoing fluxes subject to these points 2 and 3. So in some sense, this means we need to solve a maximization problem at the intersection points to determine these kind of values we need for the outgoing arcs. And this is different for each type of intersection. So I've prepared two types of intersection to explain this more precisely. So first of all, let's say that again we are in the same setting as before, thinking of Khrushchev entropy admissible conditions to solve the problem at the junction. So we really focus now on this junction problem, since we know that if we would not have any junction, we know that for the traffic flow model we have some Khrushchev entropy admissible solution. So what's so crucial about this junction? So first, to evaluate the junction problem, we need a function tau given in that way, meaning that f of tau of rho is f of rho, and that tau of rho is not equal rho for every rho in this interval, which is again the normalization. And the shape of the LWR flux function allows two densities having the same flux, okay? Let's go into the picture here. We see that if we would have a flux, we see we have here this rho and we have this tau of rho. Okay, and this would lead to exactly the same flux function. That's why we have to be very careful while evaluating now the densities at the junction. So it's a priori not clear if a flux value corresponds to this value of rho or to this value of rho. Okay, so again, we know that this tau of rho is the opposite density with the same flux. So, and we further know that we have to solve this maximization problem at the vertices and therefore need some further notation. And the further notation are given by demand and supply. So the demand measures the maximum flux at an incoming road at a junction and is given here in that way. And the supply is the maximum flux that an outgoing arc may provide and is therefore given in that way. So supply and demand are somehow upper bounds on the flux value while evaluating the maximization problem. Okay. So let's exemplarily focus on a 1-to-2 junction, meaning we have one ingoing and two outgoing roads. And then the Rankine-Hugoniot condition forces that the flux should satisfy the flux from the incoming road is equal to the flux of one outgoing road plus the other one. And we further know that the outgoing flux here is given by the distribution rate alpha 11 times the incoming flux, and the other outgoing flux is given by the distribution rate alpha 12 times this rho of the incoming flux, times the incoming flux. So, and we also know, as I told you, we have some bounds on these different fluxes in terms of the demand for the incoming flux and the supply for the outgoing fluxes. And therefore, the optimization problem at the junction we have to solve is given by this problem here, which is in fact nothing else than a linear program. And for the simple kind of 1-to-2 junction, and given by this problem here, we can write down the solution explicitly. So, and this is nothing else than the minimum of all these guys here, meaning that once we have this interpretation of this f of rho in, we can write down the solutions for the both outgoing fluxes equivalently. And this is nice to have, since now we know the solution of the maximization problem, but we have to ensure that now the flux values correspond to the right density values. Okay, so and the density values need to be uniquely defined. And that's why we have introduced the function tau to solve this problem now. So meaning that we can construct the solution on each of these arcs we have in mind. So we need, as I told you, so the connection of roads, meaning that we have to determine new values for rho for ingoing, outgoing roads, which is somehow a coupled boundary value problem. So now we have the fluxes, and we are interested in determine the two values rho in and rho out. And this can be done and leads to a unique choice for both of these values. And how to do that? Maybe we can have a look at the picture again. So in the first case, if we know that the initial data is in this regime, we know that the flux we have computed from the maximization problem now gives us the value of rho, which is given by this guy here. And the other reconstruction would mean if we have some initial data which is larger than the maximum and smaller than 1, we can compute the corresponding value for rho in this way. And the same can be done for the outgoing values. So this is the interpretation of solving the maximization problem for these special kind of incoming and outgoing roads. So this result can be generalized. So a junction with incoming and m outgoing roads. So far I've presented n equals 1 and m equals 2, but anyway, this can be generalized. And for these assumptions given here, and we have also, we already discussed, we know that we can compute now the corresponding density values to get a unique admissible weak solution. So for our coupled problems at the intersections. So to summarize so far is that we only considered these types of more outgoing than incoming roads. And of course, we should also put the perspective on the opposite. So what happens for 2 incoming and 1 outgoing road? How can we solve the maximization problem there? And this is now done by thinking of a right way parameter. So another kind of parameter, which is not the same as the alphas, which we have used for the distribution. So the meaning of this right way parameter Q is now that if not all cars can move to the outgoing road and denote with C the amount that can move, then the factor Q times C is the amount that can enter from the first road. And the rest of the proportion, namely this 1 minus Q times rho, comes from the second road. So this is something like, let's say, priority rule, and which is necessary, of course, whenever two roads go over to one road. So what we again have to think about is the maximal flow through the junction, which is now this gamma max, given by, again, expressions of supply and demand. And we also know that the set of possible fluxes from road 1 to road 2 is given by this set omega. So what's now important to mention is that the line here, Z1 plus Z2 equals gamma max, needs to be satisfied. And we also have to consider the expression for the right way parameter, which is given by this guy here. So if we now would have a look at the intersections of these two lines, we see that there's an intersection point P that might be outside the domain omega. So that's why we need to discuss two possible situations. So the first case is that P is in omega, but then it's quite clear that the fluxes gamma 1 and gamma 2 are given in that way, and the densities can be recovered again, as we have already seen for the case of the other type of junction. So there's no new problem that may occur. In the other situation, if the intersection point is outside omega, we need to solve again a maximization problem. So in the sense that the incoming fluxes are maximized again due to the definitions we have seen, and due to the restrictions that we have some upper bounds on the fluxes given by the demands of the incoming roads and the right way of parameter equation. So, and we can guarantee that the right way of parameter is exactly fulfilled, and the solution can be explicitly computed by Z1 and Z2 in a really straightforward way. So this leads again to the case that we can state a theorem for the situation we have now 2 incoming and 1 outgoing road. You may ask, oh, is there also a generalization like we did for the other type of junction? Yes, it is. But if we would have a look at the generalization, we have to introduce more right-of-way parameters, which makes it more complicated to write down. That's why I want to stick to this simple example here. But anyway, so this explains the full machinery somehow. Again, we can think or we can have some unique admissible weak solution if we compute the densities that are necessary for this type of junction in these two ways, and having solved the optimization problem at the junction in advance. So this is all we need now for the network and to think about possible applications. But anyway, let me remark how the Goodenough scheme we have also seen for a single line can be extended here in the network setting. So again, we have to set up the discretization for the space X and the time T. And this is the scheme we already know somehow. Oh, no, wrong direction. Oh, here. So, but maybe we can go through one or two special issues that might occur. So let's assume that AI equals 0. We end up with a scheme like this, and we see or we observe that there's a row -1. And this could be, for example, if the node is the origin, some internal, some external inflow, and we can replace this expression by the externally given inflow. So anyway, but if we are inside the network, so not at the origin, we have to replace this guy here by the flux computed from the Riemann problem at this special kind of junction, either diverging junction or merging junction. So that these are the two cases we have already seen. But anyway, we know the details of these two kind of problems. We have the density that might occur and can compute the fluxes again. And then this is the same machinery for the Goodenough scheme as before, to compute the cell averages and to update everything. And also important to mention is that in the case we are at the end of the line, we also need to discuss, as we have seen here for this outer discretization point, maybe we can write down some externally given flux, or maybe think of other procedures that can be applied. So finally, what are applications of this kind of network model? So for example, control problems are very popular in the case that we consider some LWR network dynamics. So for example, if you think of to find a traffic light control configuration, as we see here, so we have an intersection, many incoming and outgoing roads that might be interpreted as a graph or network given here. And you want to maximize the throughput via this particular cost functional here. And this might be constrained by the traffic net flow dynamics we have discussed up to now. You have to include the control, okay? And the control in case of traffic lights means that this U is a mapping from a time interval to a binary value, which might be 1 or 0. So in the case the traffic light is green, the control should be 1, and on the opposite, if the traffic light is red, the control should be 0. And how can we describe this kind of traffic light control in our settings? So actually it's to think of a new linear program that need to be solved at the vertices. So this is what we have seen before in a different other notion, but anyway, don't worry about this. These are the distribution coefficients again. This is the ingoing fluxes we want to maximize. And this is the flux conservation that might be fulfilled. And these are constraints on the fluxes in the case of supply and demand. So meaning, okay, you see the problem gets more involved here from the control setting. first of all, I don't want to talk on how to solve these control problem here, but anyway, you see the point that it might be included in the modeling framework we have seen, and the discussion and for the solutions is quite similar to what we have already done. Okay, I'm not talking about how to solve this kind of problem. So further considerations also might be to think about evacuation planning, to say that we need a fast and safe evacuation, and we don't want that people get in touch with some critical substance. Again, some cost functional, just a prototype. There might be other ones, and here you see there are also storages involved. And but important is that there are coefficients C in the flux function. And these coefficients are somehow costs that are determined by a projection of a diffusion advection equation given in by this equation here. So we have a spread out of some hazardous material, and then we have given some wind field, some diffusion advection of this kind of substance, and that is spread over our domain. And again, we have the dynamics given by the traffic flow. And if we look at the picture here, you see some critical material. We have our road network, and the cars need to be evacuated from this red dot. And you see, going to the right, the spread of the material over the domain. You see that cars wait, since now it's too dangerous to evacuate all the cars through the network. And once here in the picture here, the substance is not that critical anymore, the evacuation starts, and all the cars are brought to the end of the road network in that sense here. And this is again solved by using all the dynamics I presented so far. Okay, what are the recommendations I can give you so far? So there are really 3 nice textbooks for these traffic flow on networks problems. The first 2 ones are those that are the ground basis for this kind of talk I presented today, and they are written by Mauro Garavello, Benedetto Piccoli, and Ken Han, where the full machinery for traffic flow models on networks is explained very carefully. And now, very recently, there's another textbook by Alex Bayen, Maria Laura Delle Monache, Mauro Garavello, Paola Guatin, and Benedetto Piccoli, where in particular the rising control problems, I just gave you a picture, are discussed in the case of traffic flow applications. So you may think of what are current research trends. So this is a very hot topic, the case of conservation laws on networks, are still a hot topic. And one example might be the SFB Transregio, which is on the mathematical modeling, simulation, optimization in the case of gas networks. So they are mainly concerned with systems of conservation laws. So you see, this is more involved than what I've showed you so far. And of course, also very recently discussed topics are aspects of uncertainty quantifications, where from my point of view, there can be really done a lot for these kind of networks I've presented today. So far, I want to stop here and thank you for listening.
Yeah, thank you, Simone, for the very, very interesting talk. I think there's lots of clapping hands in the participant list. So are there any questions from the audience? I would suggest that you just unmute yourself and ask directly if you have any questions.
May I break the ice?
Yes, please.
Yes, so my question is, first of all, I want to thank you. It was a very, very nice and very clear talk for people, for laymen, for lay people. What I want to ask you is something which maybe is a bit out of context. So for a person coming from functional analysis, operator theory like me, I was wondering, so LWR model is based on this specific choice of your function f, so this kind of concave function. Is there any kind of maximum principle you can apply? So like if you, for instance, okay, what I was thinking of, if you fit another curve underneath this f, so for instance, a sine function, can you, does your theory behave robustly with respect to this change in the model?
What do you mean exactly with this?
You have like monotonicity of solutions. Do you have any so predictable outcome with respect to qualitative properties of your theory, or maybe even with respect to control?
So
upon change in this model, so upon change in the function you're considering.
Okay, this is, of course, as I told you, a prototype of junction. So here the situation is clear, and there are other ways to set up this kind of relation between the flux and the density. And I would say, so I have no example in mind so far where there is no maximum principle in the case that we only consider a scalar conservation law. So this is more involved if we talk about systems. Okay, so there it's not that clear what's going to happen. But here, I'm not quite sure if we talk about the same kind of maximum principle. So
so my question was, if you replace your function f by something which is like pointwise smaller, does this mean that your solution will be, I don't know, smaller or larger or whatever? Do you have still solvability or unique existence of uniqueness?
So as far as the key assumptions on the flux functions are still true, we are safe, right? So that's why I put these assumptions right in the beginning when introducing the LWR model. So there, if you would stick to the sitting, there won't occur any problems. But anyway, if you change this, it's not clear that anymore, and you have to think about really carefully about all the steps I introduced today. So maybe a good recommendation would be to have a look at these textbooks where different examples are discussed. So I'm not. So I only know. But this is now out of scope. There's the theory behind if you have discontinuous in row for the flux function and what to do then. So this is also possible. But I'm not quite sure if this corresponds to what you are interested in.
Okay, we'll look it up. Thanks.
I maybe have one simple question. So you were discussing these two typical examples with two incoming, one outgoing, or one incoming and two outgoing roads, right? And then there were, on one case, you had this distribution coefficients. On the other hand, there were this priority. And what would happen if you would have two incoming and two outgoing roads? You have to mix those two, or
yeah. This is more involved. So
okay.
So there, of course, the idea is the same. You have to think about the maximization of fluxes at the intersection, but you have to be careful to write down the maximization problem. In fact, it's not possible to solve this explicit anymore. Okay, so here in these small examples, it's possible to write down the explicit solution. that's why it's nice to have and to go through the full machinery. But anyway, then in the case of 2 incoming, 2 outgoing roads, there might be a chance to write it down explicitly, but in general, you have to solve this linear program to get the right fluxes.
But then you use both types of coefficients at the same time, or?
Yes, so you need rules.
Yeah, you need rules how to, yeah, okay.
It's more involved, okay? So it's, and of course, there's a kind of freedom to write down.
This is what I wanted to say, that maybe it's not determined, right?
Yeah, no, it's a kind of modeling freedom. You have to write down how it should look like for this kind of equation, but still ensuring that there exists a unique admissible solution at the intersection.
Mm-hmm.
But there again, in these nice first 2 textbooks, there are these large-scale examples with this kind of several ingoing and outgoing roads, and what does it mean for the solution and so on. So it gets more involved, but it's possible.
So if we have a larger network, we have to do this maximization in every vertex, actually.
Yes, right. Yeah.
Okay, so it gets huge, right?
Yes.
The computing, yeah.
Yeah, but it's a linear program only, don't forget.
Yeah, okay. Yeah.
That's why it's, yeah. And for this simple combination of 1 to 2 and 2 to 1 junctions, it's possible to write down the explicit solution. So it might be possible to construct large networks only consisting of these simple junction types.
Yeah.
For fast computation.
Okay, thanks for a very nice talk. Yeah, really.
Thank you.
Okay, I would also have a question, and I think it goes maybe slightly in the direction of the talk of Delio. So, I mean, if you have Khrushchev solutions on this, entropy solutions on the single line, you can show that the total variation of solution decays and that upper and lower bounds of the initial data remain bounds for the solution. For these network problems, do you have a similar property, or are these things somehow lost on at the junctions?
Yeah, it's a good point. I guess that that it's still possible, and there might be some notes on the procedure in the book by Holden and Riesepro on the front tracking procedure. If I remember correctly, they did the total variation estimates in the case of the network. I can check it. I have the book here anywhere. But it should work.
Okay, and maybe if nobody is currently asking questions, so I mean, in the Cauchy problem, you also have this L1 contraction property of the semigroup of the Khrushchev solutions. Do you also have this L1 contraction on networks?
Well, it's also a good question. I'm not sure. I have to check it.
Okay. I mean, I don't want to take up all the time, so other people have questions.
Hello. Can I ask a question?
Sure.
First of all, thank you very much for this nice detailed talk. I want to ask you if you have any information or studies on weak solutions with different schemes, different equations in Roger Temam's techniques or similar types.
Sorry, can you repeat the question, please?
Are you interested, or have you got studies on weak solutions of difference equations?
Difference equations?
Difference equations, weak solutions in the distribution spaces. For example, the Temam's book, maybe you heard of it. That kind of studies.
I'm not quite sure. So so far I did not work with these kind of equations. But
okay.
but there
yes, yes, please.
so if you think of difference equations, so there's a calculus for traffic in given by Jean-Patrick Lebac, who's a traffic engineer. So he wrote down some difference equations to solve this kind of traffic problems I've discussed today. But I'm not quite sure if this would be in line or in accordance to that you have said.
Yes, not exactly the same. Just you mentioned about Godunov scheme and
Yep.
Some approach, but not completely, I think.
Yeah. Yeah.
Okay. So is it possible in this kind of dynamical systems? Is it possible to difference equations and having some weak solutions and some results?
For the difference equation?
Yes, for difference equations, your type of results or.
Yes, I hope so. So in the interpretation of Lebac, I've mentioned earlier, this is exactly, again, in the spirit of a Godunov type discretization, where you measure how many cars are entering a domain and are leaving. So these kind of traffic models are called cell transmission models. And this would be probably matched the things you have mentioned.
So this is parabolic type you mentioned in this talk. So is there hyperbolic type?
Yeah, it's hyperbolic type. So these cell transmission models are of hyperbolic type, yes.
Okay, thank you. Thank you very much.
Thank you.
Are there any further questions? If that's not the case, I would like to thank the speaker again, and I would ask for the stream to stop, or at least for the recording to stop.